Now let's talk about the center of pressure. What is center of pressure? It is a location of the resultant force that would produce the same moment at the top surface. Okay, so that would produce the same moment at the top surface. We know we can replace several forces by one single force that would produce the same effect on the body, and that force is called resultant force. Okay, but to create the same effect in terms of rotation, the angle of force and its distance is also important. Okay, so the figure here shows the hydrostatic pressure distribution, and because of this hydrostatic pressure we can calculate the magnitude of force. To replace the whole system of hydrostatic force with one single equivalent force, we need to calculate the resultant hydrostatic force, which is F. Okay, so this triangular load distribution is replaced by force F. The magnitude of force of this triangular load and this F are equal. So this body, this submerged surface experience the same force as the triangular force if we apply this force F, right? So in terms of magnitude, they are the same. Now we need to find out the location of the resultant force. So where we should apply this force? At this location here, at the bottom or the top, where we should apply that? We need to put this location so that we produce the same moment effects as the distributed pressure, right? So that's another important point. This force would create a moment at this point, right? It will create a moment at any point, and let's talk about the at the surface, okay? Because that's the point we know. So what is the moment created by this triangular load at this point? The resultant force should also create the same moment, and for that we need to apply the force F at a particular location, and that point is called the center of pressure. And one thing to remember, center of pressure is always below the center of gravity. So center of gravity is the geometric center of the body, whereas the center of pressure is the uh, point where that resultant force is applied. Okay. Now you need to we need to use this parallel axis theorem. So if you have forgotten this parallel axis theorem, I would recommend you to revisit this theory. How to calculate the center of pressure? The concept is similar in all cases, but let's divide in different shapes and see the approach we should take to calculate the center of pressure. But before doing that, let's talk about the few important parameters. The first one is Hg. Hg is the vertical distance of centroid from the water surface. Okay, so from the water surface to the centroid of the object. Okay, that is Hg. The distance from the surface to the center of pressure is Hp. The area of vertical plane that is in contact with water is A, and Ig is the second moment of area. So these are the main important parameters we need to calculate the center of pressure. Okay, let's look at the first figure here. The pressure is triangular, so the resultant force acting at so the resultant force acts at 2/3 of h from the water surface, or 1/3 from the base. So that's where the force acts, the resultant force acts 1/3 of height from the base, right? So from here to here, 1/3 of h, or from water surface to here is 2/3 of h. For the second figure, here we can see the top is fully submerged, and in that case the pressure at the top is not zero. So this is not the triangular but the trapezoidal pressure force, sorry, trapezoidal pressure, right? So to calculate the force from this pressure distribution, we need to use this concept of second moment of area. So we are not going to go through the derivation of this equation, but you can see the HP, or the center of pressure, equals to Ig, which is second moment of area, divided by area times Hg plus Hg. Okay, so Hg is easy to know. Once you know the shape, the geometry, then you know where is the centroid, and you can calculate the Hg. And then once you know the geometry, you can also calculate the second moment of area and area. So based on the geometry, you can calculate other parameters, and from that you can calculate the center of pressure. So what about the inclined surfaces like this? The shape of the pressure diagram is trapezoidal again in this case, but it is perpendicular to the surface, right? So it's not the force is not acting horizontal as in the previous example. It always acts perpendicular to the surface, so it seems to be inclined like this, right? But the equation is to calculate this force and the center of pressure is similar. But the calculation for the center of pressure should be along the line perpendicular to the immersed surface. Okay, so when we calculate, we need to calculate the center of pressure along this line. Okay, and that would provide the very similar equation as in the previous example. So instead of calculating HP directly, what we do, we calculate LP instead of HP. And then we can, if you want to convert to LP to HP, that is the vertical distance from water surface to this point, we can obviously know obviously we can calculate if we know this theta angle. But first we need to calculate this LG and LP. Okay, so in this example here, this is the immersed surface. The top is H1 depth below the water surface, and bottom is H2 depth below the water surface. The force is same, right? Rho g times Hg times area. Hg is the vertical distance to the centroid. In terms of force, there is no difference, but when you calculate the center of pressure, we need to calculate LP and LG, right? So once you know this Hg, and if you know the angle theta here, then you can calculate the LG, right? So you have this triangle, this, if you know the angle theta here, and you have this triangle, and from triangle you can calculate LG if you know this Hg. And then you can calculate LP, so this inclined distance to the center of pressure, which is Ig divided by ALG plus LG. And once you know that the LG value, sorry, LP value, then you can calculate HP if you need. This is HP is the center, sorry, HP is the distance from the water surface to the center of pressure, and from this triangle you can calculate HP if required. Once you know this LP, then you can calculate HP. Pressure variation on curved surfaces is also similar. Okay, it's no different. We use the same concept, but to draw the pressure distribution diagram, we again look at the first principle. The pressure is rho g times h at any point. So at this point, what is the pressure at this point? The pressure is rho g times the height or depth of water to that point. And as you see here, this is increased slowly, and that's why the pressure also increased, and at the very bottom it will be rho g h2. Okay, so if the object was like this vertical surface, you have this rho g h1 here and rho g h2 at the bottom, right? But for the curved surface like this, again the same. At this point, rho g times this height. At this point, rho g times h again. But when you draw the pressure distribution diagram, this is not triangular or trapezoidal as before. Because the surface is curved, the pressure distribution diagram is also curved. Why? Because at every point the pressure the applied pressure has to be perpendicular to that surface. Okay, so this has to be perpendicular to this point, at this point also perpendicular to that point, perpendicular there, perpendicular here, and that's the reason it also has a different curvilinear shape. How to calculate hydrostatic force on curved surfaces? On inclined linear surfaces or vertical surfaces, we have already calculated force equals to rho g hg times area. Now, how do we do for the curved surfaces? For curved surface, the hydrostatic force is the resultant of vertical and horizontal component of the forces. So we calculate the vertical component of the hydrostatic force, horizontal component of the hydrostatic force, and then calculate the resultant, which is the final hydrostatic resultant force. So to calculate the horizontal force, Fh, what we do, we project the curved surface on the vertical plane. So this is the vertical plane, and now assume this is the vertical object or vertical surface, and we calculate the horizontal force. Okay, so that is rho times z times hg times area. Like any regular vertical surface, the component of horizontal surface on the curved surface is the same, that is rho times z times hg times area. Okay, now what about the vertical force? Vertical force is due to the weight of water above the curved surface, which is rho times z times volume, right? So that is the volume of water above the curved surface, and that will give us two components, horizontal component and vertical component, and then you just calculate the resultant of the two forces, Fh square plus Fv square, and then square root of that value will give us the force, and the resultant is tan inverse Fv over Fh. Okay, so that's how you calculate the resultant force on a curved surface.